Hello, everyone. In our team, we focus on not only robust AI theories but also applications and deployment. And there have been considerable achievements including patents, technical disclosure and conference journal publications. For theories, we have proposed robust error-correcting neural network, robust neural ODE network, and robust graph neural diffusion network. For applications, we have proposed robust camera pose regression, robust patch matching, robust GNN localization, and robust odometry. Our first work is robust error-correcting neural network. Though deep learning has been applied successfully in many scenarios, malicious inputs with human imperceptible perturbations can make it vulnerable in real applications. We propose an error-correcting neural network named DASN that resembles a set of binary classifiers to combat adversarial examples in the multi-class classification problem using error-correcting codes. We provide theoretical analysis that helps to guide the design of DASN, including the choice of activation functions. To build an DASN, we propose to design a code matrix so that the minimum Hamming distance between any two rows and the minimum shared information distance between any two columns are simultaneously maximized. Maximizing row distances can increase the system fault tolerance, while maximizing column distances helps increase the diversity between binary classifiers. DASN is complementary to other existing defense approaches, such as adversarial training, and it can be applied in conjunction with them. We empirically demonstrate that our proposed DASN is effective against the state-of-the-art white box and black box attacks on several datasets, while maintaining good classification accuracy on normal examples. For example, we conduct tests on the German traffic sign recognition benchmark under black box setting, where adversaries do not know the model internal architectures or training parameters. The traffic sign examples are shown here in the figure. An adversary crafts adversarial examples based on a substitute model and then feed these examples to the original model to perform the attack. We train ResNet20 and DASN on the GTSRB and test them on normal examples and adversarial examples. From the table, we can see the classification results are much better than the vanilla ResNet. Our second work is robust neural ODE network. Neural ODE is a network that models the network input and output as a dynamical system described by a learnable ordinary differential equation. In this work, we propose a stable neural ODE with Lyapunov stable equilibrium points for defending against adversarial attacks, named as SODEF. By ensuring that the equilibrium points of the ODE solution used as part of SODEF is Lyapunov stable, the ODE solution for an input with a small perturbation converges to the same solution as the unperturbed input. We provide theoretical results that give insights into the stability of SODEF, as well as the choice of regularizers to ensure its stability. Our analysis suggests that our proposed regularizers force the extracted feature points to be within a neighborhood of the Lyapunov stable equilibrium points of the ODE. SODEF is compatible with many defense methods, and can be applied to any neural network's final regressor layer to enhance its stability against adversarial attacks. Here we show the compatible experiment that combines SODEF and an adversarial training defense method named traits. From the table we clearly observe that our SODEF further improve the model performance under various attacks, including 3 white box attacks and 1 black box named square attack. Our third work is robust graph neural diffusion. Deep learning on graphs and graph neural networks, in particular, have achieved remarkable success in a variety of application areas, such as those related to chemistry, finance, and the social media. While aggregating neighboring nodes' information is a powerful principle of representation learning, the way that GNNs exchange information between nodes makes them vulnerable to adversarial attacks similar to the neural ODE. Neural PDE is a graph neural network that models the network input and output as a dynamical system described by a learnable differential equation. Neural PDE approaches deep learning on graphs as a continuous diffusion process, like the well-known heat diffusion process, and treats graph neural networks as discretizations of an underlying PDE. We generalize the heat flow to more general flow schemes, which are able to preserve inter-class edges in diffusion. A novel class of graph neural PDE is thereby induced. Our model is intrinsically robust to graph topology perturbations as shown in the table. In the table, we use black box, inductive attacks named SPIT and TDGIA. We clearly observe that our Beltrami flow achieve the top best under the 2 attacks. In our fourth work, we propose robust lock or robust camera pose regression network for challenging driving environment. Accurate camera relocalization plays an important role in autonomous driving. Given query images, the camera relocalization task aims at estimating the camera poses for which the images are taken. We propose robust lock that not only explores the relations between graph neighbors but also utilizes neural differential equations to improve robustness. Our model can be decomposed into 3 different stages. Given n neighboring images, a convolutional neural network extracts the feature maps of all these images. Our proposed feature map diffusion block then performs cross-self-diffusion on the feature maps. After feature map diffusion, a global average pooling module aggregates the feature maps as vector embeddings, which contain global representations of these images. Similarly, those vector embeddings are then diffused by cascaded cross-self-diffusion blocks. Based on the vector embeddings, the branch decoder module regresses the output camera poses. During training, decoding is performed on multiple levels to provide better feature constraints. We conduct experiments in both regular and challenging autonomous driving datasets to demonstrate the robustness of our proposed method. The experiments verify that our method achieves better performance than the current state-of-the-art camera pose regression methods. To further evaluate the performance under challenging environments, we inject noise into the robot car loop dataset and call this the perturbed robot car dataset. We create 3 scenarios: 1, medium with fog, snow, rain, and spatter on the lens; 2, hard with added Gaussian noise; and 3, hard training with noisy augmentation. In this dataset, the superiority of our proposed method can be demonstrated more. We visualize the output pose trajectories, where a significant gap can be seen from the comparison. Robust lock outputs more smooth and globally accurate poses compared with the previous method, which shows the effectiveness of our design. In our 5th work, we consider using landmarks to achieve robust query map retrieval. Specifically, we extract landmarks such as traffic lights, traffic signs, and poles using object detection methods. By leveraging multimodal input including 2D images and 3D point clouds, we obtain more robust and effective feature representations for the landmark patches. After feature extraction by ResNet and PointNet, we leverage graph attention neural network to further aggregate the neighboring information of nearby landmark patches, which further enhance the feature representation. Finally, for each query landmark, by comparing the features' similarity, we can find the top matched landmarks in the map database. In our 6th work, based on the aforementioned landmark matching module, we further propose GNN localization model. We follow the similar architecture as in robust matching network. We leverage the features of the matched landmark patches, and use graph attention neural network to regress the relative vehicle pose translation and output robust vehicle pose trajectory. In the left video, the objects inside of the red bounding box are the landmarks that have been detected. The purple lines indicated the graph edges in our graph learning algorithms. In terms of the accuracy, on the Oxford localization dataset, we have get less than 1 meter translation error, which is far more better than other state-of-the-art learning algorithms. We also test on the dataset collected in Singapore, where our GNN localization approach still outperforms than the baseline. Our 7th work is robust neural odometry. For the GNN landmark localization, it is useful for the scenarios with rich landmarks, such as downtown or central business district. While in the poor landmark scenarios such as suburbs or tunnels, we can use LiDAR module to achieve localization. In this regard, we designed a robust LiDAR odometry method based on the graph learning for point clouds. In our robust LiDAR odometry model, we predict the relative pose, namely transformation between 2 nearby LiDAR frames, and use the accumulated method to estimate the location. Specifically, we use the partial differential equation-based graph neural diffusion model to represent the point cloud feature robustly, and use self-cross attention and learning layers to obtain corresponding key points. At last, we use SVD module to predict the transformation. To test the robustness of our LiDAR odometry model, we exploit Gaussian noise to perturb the KITTI dataset. From the test result, we observe that our method outperforms other baselines and it almost keeps stable with the Gaussian noise increasing. We test our robust LiDAR odometry method in the KITTI dataset and run it in the ROS system. Our method can achieve around 1 meter translational error. Thanks for watching.